It might stop again. It might be full again. That's what it keeps happening. All right, well, we'll try it again. If it stops again, just let it go. So we talked about bond polarity, and we said that in a molecule like HF, the bond was polar because there was a difference in electronegativity. We drew what's called a plus arrow. The arrow showed that the hydrogen was partially positive and the fluorine was partially negative. Now we're going to do a polar molecule made out of polar bonds. I'm going to go straight to water in its shape, since we've already done that. Now I will draw its dipoles. Now, on your third exam and your final probably, you'll be asked to draw molecules in their proper shape. And it will always say, also draw the dipoles. And the dipoles will be along each bond and point towards the more electronegative atom. And I'll do it for my other bond as well. Leo?
So the proper shape is like not the tetrahedral thing, but just that the molecules are then?
So you can draw it, let's say this. If I say draw tetrahedral shape, or draw the shape of a molecule and it's tetrahedral, then draw it the one way I said. This is just an example separately, so don't worry about drawing the tetrahedral in the one way. Don't worry, it will be obvious when I want you to draw it the one way I want. And if it's not, ask. So this is fine for now, if that makes sense. All right. So now what I'd like to do is I'd like to talk about what's called molecular polarity, hence the title. And in order to do that, I have to calculate the net dipole, which equals adding up all of the individual dipoles and the net dipole is also the molecular dipole. Now, dipoles are vectors. What is a vector? Can anybody tell me?
Overall direction.
A vector has two things. It has direction and magnitude, right? And so velocity is a vector because velocity will be 55 miles an hour east. Speed is not a vector, it's just the 55 miles an hour. It's the magnitude or size. Now, when you add these two dipoles, you place the dipoles head to tail. Okay? And this is the head with the arrow, and this is the tail. And what I'm going to do is I'm going to draw these two dipoles. That's this one on the left. The one on the right is like that. And this is head to tail. And when I do that, and this is all very physicsy, and we'll stop doing it in a minute, thank goodness. But I want you to have this in your notes for physics and all other things. You go from the beginning to the end for the net dipole. Beginning to end for net dipole. And the net dipole, remember, is the molecular dipole. So what I'd like to do at the bottom now is draw the molecular dipole. Notice how it's from top to bottom, just like this one's from top to bottom as well. Okay. And this always works, because dipoles to this side. Now, if you were looking at these two, and you said to yourself, note that this one goes down part and to the right part, and this one goes down part and to the left part, and the left and right parts canceled out. That's true, and it does mean that the down parts don't cancel out. And that's exactly what this picture shows. Anyway, what I would suggest is that the vast majority of the time you can look at the arrows and tell what cancels out and what doesn't. I don't know, but we'll see. It's a process, that's for sure, and it is very important to tell polar from nonpolar molecules. Polar molecules have a net dipole, have a molecular dipole. Nonpolar molecules don't. So, and we'll talk about that as we go. Good. So, what I'd like to do here is draw the left and right portions and say they do cancel out. The down and down portions add up. And vector addition, by the way, is one of those things that once you know how to do it, pops up in more and more places than you think. Sort of the new car effect. When you buy a new car, all of a sudden everybody else has the same car. That's what I found. Any questions about this? Then we do more. Carbon tetrafluoride, a nonpolar molecule made out of polar bonds. Here's our process for this. Everything starts with the Lewis structure. Lewis structures have all the electrons in them. There's the Lewis structure. Now let's draw the shape with dipoles. This is tetrahedral. This would be a great one to put on your third exam. There's the shape at least, drawn the one way. I think that's what I'm going to do too, is I'm going to write on your third exam, oh, this might be too much of a giveaway then. It says draw whatever shape this should be the only way you're allowed to. Would that be too much of a giveaway? No. All right, now red dipoles. I have two atoms, carbon and fluorine. Fluorine is more electronegative, so the dipole points towards it. Four dipoles. Are you going to have an electronegativity chart with you? here's what we know about electronegativity.
It's a general thing.
Decreases, and the numbers that you will need for specific values of the electronegativity will be given to you on your conversion equation sheet. The classic one is oxygen and chlorine. They're diagonal, so it's not clear. And then you'll have them as numbers. All right. So now we have 4 different arrows. Dipole or vector addition, very complicated. But if you did all of these dipoles, 3 of them go out and down, meaning that these 3 have a net downward dipole. This 4th one goes straight up. In fact, they do exactly cancel. That's hard to do. Do you believe me? I have one person who believes me.
Yes.
2 people. We'll get there. All right. So, in reality, when you start getting, I would suggest to you that it's relatively straightforward to see that these arrows don't cancel out. Let me do another example where they do exactly cancel out. See this one? Each of these double bonds has a dipole. Oxygen is more electronegative. Those are in exactly opposite directions. That's easy to see that they cancel. That's what I'm trying to suggest anyway. Maybe you believe me. All right. These ones are hard, and so here's what I would like to come up with. A general rule that says anytime the central atom is surrounded by all things that are exactly the same, here I'd like to be careful. An atom is different than a pair of electrons. Comma, the molecule will be nonpolar. The molecule will be nonpolar. What that means is that even though there are 4 different dipoles in this molecule, since they're pointing in exactly opposite directions, they will exactly cancel. This is a nonpolar molecule made out of polar bonds. Questions about that? This is a polar molecule made out of polar bonds. According to that rule over there, there are 2 things that are different. H's are different than pairs of electrons. That's why this is polar. Okay. It is true that boron trifluoride is a nonpolar molecule made out of polar bonds. Boron, if you remember, has only 3 pairs of electrons around the central atom. Don't worry about that one too much, it is true. Ammonia, I will leave that to you to do. Ask me questions about it. Let's go to C2H6, otherwise known as ethane. Ethane's kind of interesting because each of the carbons in it is a tetrahedral atom or has a tetrahedral electron geometry. I'm going to draw it something like this. If I were to draw the dipoles, which atom is more electronegative? Hydrogen or carbon? Carbon is more electronegative, so the arrow has to face towards the carbon. And there are 6 arrows. Technically, they should all be the same size. I've tried to do that, maybe with limited success, because they have the same difference in electronegativity. My question for you, is this a polar or nonpolar molecule?
Nonpolar.
It is nonpolar. Why?
They're identical on each side. They're equal on this side, equal on this side.
They're equal on this side, they're equal on this side,
They're symmetrical.
and it's symmetrical. Those are all good reasons why this is nonpolar. In this particular molecule, yes, we have these 3. If we did the vector addition, these 3 would exactly cancel these 3. If we think about this rule, anytime the central atom is surrounded by all things that are exactly the same, well, that's more complicated. However, the symmetry of it does make it so that whatever's on this side and whatever's on this side. So there's not, it's like the center of the molecule. This is a nonpolar molecule. However you come to that is fine with me. Now, I will have an additional rule for my class. And then actually this is everybody's rule. Anything made out of only carbon and hydrogen is nonpolar. And in fact, the way that some people teach it is that if the difference in electronegativity is small enough, they're nonpolar. That's to deal with this case as well. Hydrogen is 2.1, carbon is 2.5. Anyway, there are various ways to get to this point, but anything made out of carbon and hydrogen only is nonpolar. Because, and it gets complicated, but whenever the dipoles are on one carbon, they will cancel dipoles on another carbon. Questions? What are you doing? That's the end. Bodhi, question? So, I hate to do this to you, but we're going to stop there. We're going to pick up on the next set of lecture notes on Monday. Let's see. Monday, Wednesday. Monday. We are down to 4 lectures left. One lecture I'm missing. Another lecture we have a 3rd exam. And then we're done for the semester. So 4 lectures and count.